Do I have to? Yeah, I share my screen now, right?
No, just leave it like that so I can introduce you.
Okay.
Yeah, you've got 56 people. Whoops, how did that happen? Okay, we'll just wait a couple of minutes to let the attendees log in. We've got.
So here it says, do you want to stop screen sharing? Do you want to continue? So
yeah, please don't do anything. I'll do it. Yeah,
okay.
Just sit back. Everybody's watching you now.
Well, I'm standing at my adjustable desk. This is the greatest thing since liver pills.
Yeah. Well, everybody, I'd like to welcome you to yet another EMinar. It's Wednesday, it's EMinar Day, and it gives me great pleasure to introduce a long-time friend and colleague, Doug Oldenburg, who's going to talk to us about the fundamentals of inversion. And we had a fabulous registration for this, and I hope all of you come in. So let me just, before I introduce Doug, I'll just go through the upcoming EMinars. So next week we have Lindsay Hege, who's currently at Berkeley but moving to UBC. And Lindsay worked for a long time with Doug, and basically the way I like to explain it is she wrote Doug's brain into code. And she'll tell us about SimPeg and GeoSci. And the week after that, we have a fabulous presentation from Connie Manacero, who's going to talk to us about a paper that's just been published on an approximate method of getting a 3D forward solution so you can then do probabilistic inversion of MT. We depart then a little bit from modeling and inversion. We go to Julianne Hubert, who tell us about space, weather, GICs, and MT. And then we come back to the world's most academic used 3D inversion code from NASA Megbel, who gives us a talk on ModEM. Followed directly by Vladimir Prusiev, who talked about neural networks, inversion using neural networks. And then Kerry Key, another code talk. Kerry will tell us about his MAR2DEM code that's freely available. He'll walk us through the code, tell us about concepts. And following directly, we have Randy Mackey on geological consistent inversion. And then Malcolm Sambridge, who's the Benno Gutenberg medalist for the AGU in 2020 and the Benno Gutenberg medalist for the EGU in 2021, who's going to give us a very general talk about inversion. So a fabulous lineup of inversion talks coming up. So just to remind you, on the EMinar webpage, you'll find the registration links for upcoming EMinars. You'll also find videos and presentations of past ones. And you're on a webinar, so you change where your sound comes from. You can chat to the panelists or you know, the audience. You can raise your hand if you want to speak towards the end, and then we have question and answers. And towards the end, Doug will answer your questions. So very quickly, today is wonderful. We're going to hear Doug talking about fundamentals of inversion. And I probably don't need to tell you about Doug. He's one of the foremost geophysical inverters globally. He's currently now emeritus professor at UBC. He's director of GIF. As you can read, he is focused on inversion of solving all sorts of applied problems. And if you go to an SEG, every second talk uses Doug's codes. He's made geophysics more accessible and engaging. That's certainly true. It's been a wonderful asset to geophysics for many a long time. And just to show you how long a time that's been, here's a picture of Doug taken in 1991 in Hussong's Cantina. Together with Steve Constable and Ian Ferguson and myself, Kathleen de Groot Hedlin and Steve Park, Dave Burners. Okay, right, Doug, I'll stop sharing and hand it over to you now.
That picture kind of brought back a little things. Yeah. Whoopsie. Did I lose? Oh, there we go. Oh, okay. So thanks, Alan. That was a very generous introduction. I appreciate that. That's a kind of an old picture too, but does say something about how long we've been around. Look, I want to give a shout out to you. These are trying times, and it's kind of transformative. And your webinars here have just been like a breath of fresh air. So for all of us who are kind of secluded, it's something we can look forward to. And the talks have been great, and I really want to thank you for kind of putting all of this together in your incredible energy for doing that. Hold on. There we go. So that said, when you asked if I'd give something on fundamentals of inversion, my initial reaction was, yeah, we should do this. This would be good. And part of the reason for that is that with my two co-authors, Sagi Kang and Lindsay Heggie, we traveled quite a few places around the world with the SEG disk about electromagnetics. And as part of that, we had people show what they were doing for the use of geophysical inversion and electromagnetics. And it was really interesting because we're sitting there. People are using very sophisticated codes. ModEM is very prevalent, but a lot of others too. And they're showing results up on the screen. And honestly, we're looking at ourselves and we're saying, what is that? There's just no way that can be geologic. I mean, there was just all kinds of anomalous blues and red dots and stuff that they were interpreting. And it's just not right. So most of that, and if you talk to them, they seem to they got it all down. Like, oh yeah, well, we're minimizing an objective function. It's got a misfit. It's got a regularization term. Got Tekanoff in there. They've got all the words. But then when you really try to drill down a little bit, you find that there's a lot of things that are missing. So that's a motivation for kind of doing a talk like this. The trepidations, which I have a little bit, is that this is a very experienced audience. And so I'm not sure that a lot of this stuff is going to be particularly new. But I do want to introduce my collaborators. First of all, there's Sagi Kang, who is a postdoc at Stanford University, a brilliant data scientist, and is really interested in water resources and applied problems. Lindsay Heggie, who is project lead for SIMPEG. You'll hear a lot more about that tomorrow, as well as electromagnetics and just applied geophysics in general. I'm really pleased. Lindsay is returning to UBC next July. So this is exciting for us. She's going to be back here working on applied problems. And if there's things in this talk that you really like, whether it's the Jupyter notebooks or any of the slides or any of the things that are doing, you could probably thank Sagi and Lindsay for that. There's two other people that are important in this talk. One of them is Dom Fournier. He was a PhD, he's now working in industry. And he's done a lot of work on sparse inversions. And Thibaut Astic, who is kind of launching what we feel will be the next direction of sort of research for inversion at the geophysical inversion facility. Oops. Huh. Good. Might be worth just a bit of background. I'm very ancient. I did my PhD in geophysics at Scripps Institution of Oceanography, and was a student there. And at those days in IGPP, you could actually have a very palatial room, which I did. So I had a palatial office with a big door that overlooked the ocean and red carpeting and things like this. And it was really nice. But the thing that made it was that right next to me, the office was Freeman Gilbert, Next to him was Bob Parker, and next to him was George Backus. So these are the three icons, I feel, the three pillars for geophysical inversion. They taught me everything that I know, and I've kind of built upon that ever since then. And what I'd like to do is show you a timeline here for applications of inversions. So in 1975, the level that we're at, we could basically do like a 1D DC resistivity MT, maybe 50 variables. 10 years later, workstations come about and we could do 2D DCIP, maybe 1,000 variables. Another 10 years later, we could start to do 3D gravity and magnetic problems with 100,000 variables. Another 10 years, basically 3D forward modeling in time and frequency domain EM, and work with a few sources. The big revolution came here just shortly after, where we could start to work with direct solvers, and then of course multiprocessors. So those were the two that really launched the serious application of 3D frequency and time domain EM. So the point about this is that I think the fundamental aspects of how you think about the inverse problem, how you work with it, was actually established really early on by Bob and co-workers. And it's really the advances in computing power and some numerics with respect to inversion methodology that kind of allow us to solve most of the problems that we do today. The talk I want to give today, divided in a couple of parts. I want to talk a little bit about just numerical implementation, especially for the forward problem. For the linear inverse problem, there's a really nice problem that's connected with something practical. It's called the induced polarization problem. And then there's a nonlinear inverse problem, DC resistivity. And then there's the essential aspect of like, okay, how do we grapple with non-uniqueness and include other information? So those are kind of 4 parts. So what's our goal here with the geophysical experiment? We've got an Earth, some physical properties, maybe conductivity, permeability. We want to find that. So we have a source, put some energy into the Earth, we measure some fields, and we get some data. The example that I want to talk about is this DC resistivity problem. So we've got 2 electrodes, A and B here, which put current into the ground. And when you turn the current on, okay, there's an immediate rise in the voltage. So what happens is that the current, when you put it, into the ground, gets sucked into conductors. It goes around resistors. And in order to do that, there has to be some charges that are built up on here. And those charges then give rise to an electric potential that is seen at the surface. So that's the basics of the experiment. And if we look over here, this is what happens when you turn the current on. You get an immediate rise in voltage. But if you have another phenomena, the ability for the object to accumulate charge as a function of the current going through it, which is called induced polarization, then the voltage will continue to increase in here, if I can get my cursor back, to something that looks like that. And eventually for the DC resistivity problem, we're going to take this voltage right here. If we turn that current off, the voltage immediately drops, and then those polarization charges just gradually decay away, and we can measure a secondary voltage out here, and that's going to be the IP response. What makes this problem attractive for this particular talk is that the IP part of this is actually a linear problem, and the DC is a nonlinear problem. So we'll work with those, and yeah, as far as a data set for collection, because you can collect both of those data at the same time. The example I'm going to show is a field example. It's from Australia. And here's a cross section of it. It's got some limestone, resistive limestone at the top. There's a lot of carbonaceous stuff at the bottom. Interesting, the important thing is that there's a mineralization zone, one that goes in through here and one that goes in through here. So those used to be connected, but they are, they've been disconnected by a fault. So you can see that fault here. So this mineralization zone, project's known as Century Deposit, is actually quite valuable, and be nice to be able to find that. This work has been published by Mutton in 2000, but really a lot of the primary work, shout out has to go to Yagwa Lee, who was with me in those 1990s, and he did a lot of work on really discovering this project. So what do the data look like? So this is the DC resistivity data. So this is a pseudo section. The end spacing is down in this direction. So we've got dipole spacings of 100 meters and n equal 1 to 7. Here's our DC resistivity pseudo section, and here's the IP. So, you know, it's data. What can you say? Doesn't really look very geologic. And the question is, so what Earth model actually generated those data? So our statement of the inverse problem is really as follows. So we're given a set of observations, dj, could be n of them, and some uncertainties for each one, epsilon j, and our ability to do forward mapping. And with that, our goal is to try to find an Earth model that actually gave rise to the data, so the usual thing. I'm going to make a little bit of use of these diagrams here, which are kind of conceptual cartoons, but this one illustrates the forward mapping where we start from some element in model space and go to data space, and then the inverse mapping is going the other way. So this is what we want to be able to do. And the challenge with the inverse problem, it's ill-posed. It's non-unique, and it's also ill-conditioned. And any inversion algorithm at the outset has to address this non-uniqueness of that solution. Just to show you how kind of extreme this can be, here's a DC resistivity experiment. So this is a pole dipole, and there's a conductor and a resistor prisms here buried in a uniform background. And if we take data over here, we get a pseudo-section that looks like this. So you can see that there might be something kind of associated, a little bit of pantlates there. Then we take those data, we invert them, and we get a recovered model that could look like this. So we got some red here and some blue. So we're, you know, kind of getting some information out about that. However, it's possible that we could have had this model here. So this is another model, fits the data to exactly the same amount, but it looks very different. Still a bit of red and blue. And here's yet a different one that's looking crazy like this, still kind of reddish and bluish here, but doesn't look like the Earth at all. And here's another one. So the point is, this is just at least an example of how the mathematical non-uniqueness of the problem can come to the fore. So we clearly have to constrain. And that means that the inversion needs to incorporate geophysical data as well as a priori information and output something. So what's available? Well, sometimes we know geologic structure, kind of the general feel for what it should be. There might be geologic constraints, know of a particular fault, some area, reference model bounds, multiple data sets, physical property measurements. All of these things carry information about the model that we're looking for, and we'd like to incorporate them. So we need a framework. And there's two popular frameworks that exist. There's a Bayesian probabilistic framework where everything is really couched in terms of Bayes' theorem. And there's also a deterministic or Tekanoff approach where instead of trying to find a probability, we try to find a single solution. And we do that by formulating an objective function that combines a misfit term and a model norm and some weighting parameter, beta, which is a trade-off parameter, or Tekanoff parameter. So, and perhaps you've got some bounds. So this is the other approach, and that's the approach that we're going to use. The inverse problem really has a lot of components that are associated with it. And each of these are tied together, and you need to be sure that you do step one carefully before you go on to step two. And I think one of the things that's really helped us is to have a flow chart, just to kind of decide, like, okay, where are you on this scheme of the inverse problem? And we've got some inputs in here, and we've got all of the other parameters. And really what we want to do is step through this box, check to make sure that we're doing as well as we possibly can at each box, and then move on. So let's first look at the inputs here. So what have we got? We've got field observations and error estimates. So what survey did you use? What were the sources, the receivers, the distance? What was the processing that has been done? And from the point of view of data, has there been any normalizations? So that's first part. The other part that really needs to have a lot of time and effort spent is on the building in all of the a priori knowledge that you have. So that might be assembling petrophysical information, geologic information, everything that you got. And what I want to emphasize here is that at this stage, build a reference model. Put your neck on the line and say, okay, this is kind of what I think the Earth is like. That's going to be useful for a couple of reasons, but one is that it even just helps formulate your question about what you're ultimately then going to try to find from doing the inversion. The main thing in this, or an extremely important thing, is this central box here, which is the ability to forward model. This guy is crucial. If you can't solve the forward modeling quickly, rapidly, accurately, you're going to have a hard time doing the inversion. So let's just look at that. So you're faced with some equations, maybe Maxwell's equations, and then like, okay, how do I forward model? What's my approach? Well, you've got a couple options. You could do an integral equation approach, or you could do a differential equation approach. So both of those are valid. They're used extensively, and you can choose for whatever reasons, whichever one you like. Well, irrespective of that, you need to contend with a mesh. So you're going to take these functions that you're dealing with in the differential equations and convert them to numerical vectors and matrices. So you need a mesh to do that. And things that you'd like to do or have for that mesh is it easily kind of conform to the structure that you're working with. So if you've got topography, or if you've got particular kinds of geologic geometries, it'd be nice to have a mesh that emulated that. Another thing that's crucial is just the size of the mesh, the number of cells that you have, because you're going to have to solve a matrix that's somehow connected with the size of that. And the smaller it is, the faster you're going to be able to go. And then we need to be able to discretize the equations on the mesh. And ideally, you want to have that discretization done so that that forward problem is easy to solve. So sparse matrices are nicer in that regard than full dense matrices. And you want to be able to visualize the fields and the models. So those are kind of the things that you want to have, but some of them are kind of contradictory to each other. If you try to make the number of cells too small, then maybe you can't conform to the structure, and you might also get very poor accuracy out. But those are the lists to kind of think about. So what types of meshes are there? There's unstructured meshes, and you're going to hear some more in the EMinars about that. So in these, they've got some appealing things there in the sense that they can kind of model complicated geometries and make something that can look geologic. There's structured meshes, or sometimes you call them just tensor meshes, that have kind of uniform sizes in X and Y and Z, and could give rise to a mesh that look like that. And then there's semi-structured meshes that, like an octree, or in 2 dimensions, quad tree, that are prismatic, but the size of the prisms can vary. So if you have topography, for instance, you could have small cells there, and if you've got an object here, you could have small cells. And away from that, you can have very larger cells. So this is very efficient from the point of view of just bringing down the number of cells that you have. So all of the things then to consider in here are the geometry, your ability to visualize things, how easy it is to actually generate the discretize everything on it, the ease of programming. Can you handle infinity, cell size, changes of cell size? All of those things play a role and need to be considered. And lastly, we have to solve these things. So we can work with a finite difference method, finite volume method, or finite element method. The complexity of the system increases as you go down. We're going to use a finite volume method. But it doesn't really matter which of those things you use or how you get there. At the end of the day, whatever you've chosen, you have to solve a system. AU is equal to Q. So Q is the right-hand side, your sources. U could be potentials or fields or fluxes, and A is your forward modeling matrix. So you've got to solve that. And then the question about solving, okay, well, what's the size of this? If it's small, then you just use SVD or backslash or some kind of equivalent. If it's intermediate, maybe you can have a direct solver. Like A is, you could use a Cholesky decomposition or an LU decomposition. If it's very big, you need iterative techniques. So again, there's a whole range of possibilities in here. But the important thing to remember is that that forward problem not only needs to be solved once, it needs to be solved a lot of times. And if you consider an airborne time domain problem, then the forward problem, maybe you have 1,000 transmitters, 50 time steps, that's 50,000 solves. And then if you invert those data, and you've got maybe 20 Gauss-Newton iterations, and you're using a CG solver, you could have 20 million solves that you need to do. So that means your forward problem needs to be efficient, and you probably need a lot of processors for big problems. Once you've got all that set up, there's a couple of sanity checks that are important. Of course, you're going to test your numerical results against semi-analytic or analytic solutions, half spaces or spheres. In doing that test, you can often get some idea about what the numerical modeling errors might be, or at least a bound to them. And that can be useful later when assigning uncertainties in the inversion. And then the other thing is that you forward model your reference model. Okay, so you've already figured out a best reference model that you've got. Forward model it, and then look at the data. And you check, okay, do I have normalization errors? Is Z up when it should be down? Do I have coordinate system problems, X and Y? I mean, all these things. Because if you miss something at this stage, honestly, you spend a lot of time and you're totally screwed up. So just a few sanity checks to get there. Okay, so that seemed like a long time to go through, but actually within a practical inversion, sometimes most of the time in the inversion is actually spent just sort of setting things up. So it's worthwhile going through that in detail. So the next step is to define what inversion parameters we really want to solve for. So, we might have, electrical conductivity in the cells, but maybe we want to group the cells, or maybe we want to solve in the inverse problem for log conductivity or something. So we could have all kinds of representations for what we really want to solve for. And we're going to put all of those into this quantity m that is the sought function. And then using our Tekanoff approach, we're going to try to find a best solution by minimizing this particular quantity. So it's got two things here, misfit and a model norm. Let's just look at those. So first of all, the misfit, just commonly known to virtually everybody, but we're step through it here anyway. The observed data that we're going to work with is given by our whatever our numerical forward modeling is, plus some noise. So then the question is, what is this guy? Well, he actually includes a whole host of things. I mean, it could include dimensionality errors, 1D versus 3D. Could be incomplete physics. You've neglected mu in an electromagnetic problem, just worried about sigma. Or it could be discretization errors. So it could be modeling errors, or it could be, the other kinds of noise that we tend to think of, like instrument noise, sensor noise, survey parameter errors, wind, whatever. So the bottom line is that the true statistics of the noise is actually really complicated. And in practice, we're just going to assume that they're Gaussian with zero mean, some standard deviation. And, and in spite of the crudeness of that, we've gone a long ways over the last few decades by just using that. So in dealing then with, with uncertainties, if we have a random variable x that's normally distributed with standard deviation 1, then sum of squares of that defines the chi-squared criterion, which everybody's familiar with, I think. And then the expected value of this is n, and the standard deviation is 2n. So that now allows us to set up a misfit function. So we're going to use a data misfit, that's the normalized sum of squares, and we can discretize this, and we'll introduce a matrix WD, which is 1 over the diagonal elements of the guy. So that means that phi d can be written in this quadratic vector matrix form here. So that's our misfit. And now the expected value of phi d is approximately equal to n. So we don't really know what epsilon j is in any problem, but as a rule of thumb, kind of thinking about it in a framework that the uncertainties applied are percentage of the data plus the floor, that's a really good place to start. So the next step then is the model norm. Let's remember that in general, we're trying to find functions. So the density or electrical conductivity, these are functions. So it's best to take, represent the norms as functions and then discretize. So we got all kinds of choices. We could have just the difference between the model and a reference model, or first derivative. Generally, we sort of gang these guys together. So we could take something like this, which we could, this element could be a smallest model. This is sort of a flattest model. And we're going to weight them with hyperparameters, alpha s and alpha x. And then when we discretize that, we end up with a set of quadratic functions here that, well, look like that. So now, next step is to actually perform the inversion. So let's look at a linear problem. So if we transform that linear problem, discretize it, we could write that as some matrix G, whoopsie, times M equal D. So G is our sensitivity matrix or forward modeling matrix. And if we generate our objective function, here's our misfit term that we just talked about. And then here is the model norm here. So we've got a quadratic here for the misfit. We've got a quadratic for the model norm. So the sum of quadratics is quadratics. So if we sketched out phi of m as a function of m, we'd see it kind of looks like this. So it's got, a single minimum. And if we're going to try to find that, then we're going to be at some place. We'll take the gradient. So if we differentiate this objective with with respect to the elements m, we get a gradient. And then we're going to set the gradient equal to 0. That would define this point here, the minimum. And doing that, we get a system of equations that looks like this, which could be concatenated into something like H, which is this matrix here, M, the thing we're looking for, and B is a right-hand side. So that's our system for linear system. We could go ahead and we can solve that just by applying the inverse of H to this right-hand side. The thing that I really want to concentrate now on is the role of the Tekanoff parameter beta. So we've got a misfit plus a model norm weighted by this parameter beta. So if beta is approximately 0, then we kind of reduce it. So then phi is just equal to phi d. So that means that we're just trying to find that model which fits the data as well as possible. Alternatively, if phi approaches infinity, then we don't care about the misfit, and we're just trying to minimize this quantity. So let's kind of get a sense of what happens here as beta changes. So if we started with a really high beta, we're going to plot phi d on this axis. Beta is here, so there's high, low. Very high beta, we get a very high misfit. As beta decreases, then the influence of the misfit becomes larger, and in the inversion, we get successively better or smaller misfits. So we end up kind of coming down this curve. And if we kept decreasing it, we'd end up with something perhaps that looks like this. So the phi d will continue to decrease as beta decreases. Correspondingly, what's going to happen with the model norm is that it's going to start off being very small, because that's what we're minimizing. And then it's going to increase, because as we decrease the misfit, we need to put more structure in. And so that's going to increase the model norm. And what we see is that at some point there's a lot of structure, there's a lot of model norm coming in order to fit the data. So those are how things work as a function of beta. And in our particular case, if we did have a target misfit, have a line across here, and so this is like 20 data, so this would be the point here. So the kind of critical beta that we'd be looking for is something in the order of 100, and it would be at this particular point on this curve. The other way of plotting this curve, which is the way we'll use most often, is we'll generate what's called the Tekanoff Curve, which is a plot of the misfit versus model norm. And now if we plot this function in here, at these very high values of beta, we're up here, you're basically having a very large misfit. Structure is added, we're reducing misfit. So as we're coming down here, we're always reducing misfit, increasing structure. Here's our chosen point, and we could come along here and eventually go through there. So that's sort of the idea. And we've got an app. Now, I'm really excited about this. This is an app. It's available in Curve Node, so something that you can actually use after, well, you could use it right now, or after this talk. And Curve Node it's a new technology, which we've just discovered in the last month, but it allows us to develop Jupyter notebooks without having to go through GitHub and pushing and pulling. And it allows people to interact with these notebooks, either by using them or leaving comments, or if you're allowed to make alterations, you can actually change them and add stuff. So we're doing a lot of work now on transferring things into this, into Curve Node. And I'm just, incredibly excited about it. Lindsay's going to talk a lot more about that next week. But anyway, I'm going to show you the Jupyter app. So here's the Jupyter app hooked up through Curve Node. And we're just going to kind of step through and see what how this tutorial works. It's divided into two parts. The first part is really the forward modeling. So we're going to create a model M. So that's going to be our Earth. Then we're going to have an experiment. So that is essentially generating our matrix G. And then we'll generate some data, just product of G times M, and then we're going to add noise. So that's the first thing. So how are we going to set this up? We're going to use just a simple linear problem where the jth datum is some inner product of a kernel function with the model M that we're looking for. And to choose the kernel function and try to have some sense of reasonableness to it, we've chosen something like this. So it's a cosine function where the oscillations are controlled by the parameter Q. And it's also got an amplitude function, exponential, usually decaying, could increase, that's controlled by P. So there's basically, for each datum, two parameters, an amplitude controlling parameter and a oscillatory parameter. We're going to discretize that, and when we do that, we end up with a sensitivity vector for the model parameters. The full sensitivity matrix G is just made up by each of these G's being a row of that matrix. So this is an N by M matrix. So N is the number of data, and M is the number of model elements. And then the forward modeling is just given by that matrix vector product. and then we're going to add some noise to it. Okay, so that's kind of where we're going to go. And just a second, let me just rerun. I think I was playing around. That works. Okay. I didn't leave it in the state that you would see it when you open this up, so I think it'd be nicer to do that. The first part is, doing this. Okay, we want to develop something. So, how about a boxcar and a Gaussian? The little app, it's got some widgets here, just allows you to change the various parameters. So the parameters that you can vary are the location of the boxcar, the width of the boxcar, and the height of the boxcar. So right now, the amplitude of that is 1. If I wanted to make it 2, then could go like that, or you could shift it or do anything you want. And the same with this for the Gaussian. If you wanted to make it a whole bunch narrower, then you could control the stigma. Okay, so that gives you some flexibility on generating the model. So the next thing is the physical experiment. So here we have an artificial experiment, and we've got our kernel functions, which were sinusoids. And so they actually look something like this. So you can have a number of them. So in this case, there's 20, but maybe wanted to just have 8 of them. So you can choose how many you want. And then the p-values control what the amplitude is, and the q's control the oscillations. So there's large things. You can play around and get all kinds of different sort of combinations here. We're not going to bother doing that. What we're really interested in is now doing a simulation of the data and adding noise. So I'm going to go down to kind of a composite widget for forward modeling. It's going to show you something that you've already seen. So it's in 3 columns. The first column is building the model. So we've kind of shown that. The second column is building the survey, or building the kernels or the G matrix, and we've shown that. And then the third is your ability to add noise. It's a percentage plus a floor. You can put in whatever you want. 0.03 default, we'll do that. And so these are now the data. So what's happened here is that this first datum that we have, 0.45 or whatever, is the inner product of this first kernel, the blue, with this model here. So you can see the kernel function is mostly positive, close to 0.01. So if you did that product and then integrated, you'd get a pretty high value. But if you look at one of these oscillatory kernels and do the inner product of that oscillatory kernel with this, you get a much lower number. So the data, you can already intuitively see that, yeah, okay, we should start off high and might be kind of wiggling and down there. So those are the data, and we're going to add a little bit of noise to them, and now we have something that looks like this. Okay, we're now set. We've got our data. We're all set now to do the inverse problem. So here's our objective function has a misfit, which we'll have like this, and it's got a model norm, which has got a smallest model component to it, as well as some flatness associated with it. And then we're going to control everything by this quantity beta. And what we're going to do is we're going to minimize this just a whole bunch of times, and each one with a different beta. So we're going to select a range of beta, and then for each value of beta, solve this minimization problem. Okay, so this is on the next panel. It's, in fact, this thing is already run, and I'm just going to kind of show you the results. I'll first talk about the parameters for generating the model. So we need to assign uncertainties to the data. So I'm going to assign uncertainty 0% and 0.03, which turned out to be what the true representation of the data errors were. I'm also going to have a reference model that's 0, and I'm going to specify alpha s to be 1, alpha x to be 0. These are choices. You can play around. The beta, you never know what beta is. It's the most fleeting parameter, and what we're going to do here is have a minimum value of beta and a maximum value, and then we're going to discretize it in a certain number of points in beta, and we're going to do that logarithmically. So what we're going to see is, in this case, there's going to be 81 minimizations to give rise to 81 solutions. So here's the default. This is how the algorithm would come up when you're working with it. And what are we seeing? So here's on the model, we've got our true model. And then the orange here is the recovered model. So it's kind of not bad, right? So we've got this block in here, and we've got reasonable representation that's coming from, kind of smooth, but it's okay. And even the Gaussian, where the kernel functions are dying off, we actually still get something. The thing that is important is, though, how have you fit the data? And we can plot the data in a couple of ways. One is the observed and the predicted data. So the x's here, the predicted, observed have the bars, and looks like we've done pretty well. The diagram that we find extremely useful, however, is actually plotting normalized misfits. So what we're doing is we're taking the misfit, dividing it by the standard deviation, and then looking to see how these things are. So ideally, the results here should be points that are Gaussian distributed with 0 mean and unit standard deviation. And that's pretty reasonable. This is plus and minus 1. So like 66% is in there. So that's actually pretty good. Okay, now let's come over and take a look at what's happening here. And I'm going to do something. I'm going to unclick the run button. I'm going to click the explore button. What that is going to do is allow us to explore the solutions at any particular value of beta. So in fact, if I just a second here. So when beta when beta is really small, here's the model that we get. There's barely anything at all. The misfit, so that is the black line here, the phi d. So here's the point that corresponds to the 12th beta value. And you can see that there's some reduction in misfit, but not very much, and that the model norm is still pretty small. If we move on that, we're gradually going to misfit, do better misfits, and as we get better misfits, also increase the amount of structure that we've got. So this is a curve that I was explaining earlier. I'm going to flip back to the Tekanoff curve itself. So if I combine those two previous curves, then we're going to have the Tekanoff curve phi d as a phi m. So this is an invaluable curve to take a look at. And we're going to step through and see what is actually happening to the model, the misfit, as we change beta and as we go down this curve. So we go 18. So now we're down at this particular point here. Actually, the misfit is still huge. It's 120. We're starting to build up structure in here. Take a little bit of a delay. If I go to 27, we've reduced the misfit to 32. Whoops. It's moving. So as we go down the curve, you can see what's happening. I'm getting more structure being built up, and I'm kind of partway down the curve. What gets to be very illustrative is what happens as you come farther down the curve and reach that critical point, the kink. So here we are. This is a pretty sensitive point. So we're at now the 31st beta, and we've got something that looks like this. So we're still kind of okay. But you'll notice now as I go farther down that Tekanoff curve, we'll watch what happens to the model itself. Because now what we're doing is fitting the data just ever so a little bit better, but at the expense of having a lot of structure. So this is a misfit of 7.5, 7.1, 6.8, 6.6, 6.4, 6.2. So now we're just rounding that corner. 6.1. 6.0. So you can see how these oscillations are starting to build up in the model. So now we're still at 6.0, and now we're at 5.9. It's still 5.9. So the real take-home message here is as follows. Just summarize this quickly so I won't go too long. But so you plot the Tekanoff curve, and there's two areas of this. One is where you've got a steep slope. You're reducing the model norm or reducing the misfit, but you're not changing the model norm very much. So that's signal. You're working with signal in here. On this leg here, you're working with just fitting the noise. And so you want to be to the left of this kink or really right at that kink and be in there. The other thing that's kind of interesting is that the expected value of the misfit equal to n often lies above the kink. So as a first shot, that's usually our target misfit, approximately equal to the number of data. But often you can do a little bit better, and you should always, while you're doing an inversion, carry out the inversion at lower, some lower values, and make sure that you kind of get through this sort of kink part in here. And that will give you a lot more confidence, especially when you look at the models as to what's happening. Anyway, you'll have fun playing with that. Every realization is different, and you'd be surprised at how many interesting things come out of that. So now I want to go back. So that's the linear problem. Now we're going to do the IP problem. So in the IP problem, we're going to introduce something called chargeability. This was done by Siegel in 1959. And effectively, if something is chargeable, it effectively increases the resistivity. So we have a relationship between chargeability and resistivity. And any IP datum can actually be written as a sensitivity function times chargeability. And that sensitivity function is actually obtained from the Dc resistivity problem. So the final governing equations are that the IP data are J times eta. So that's a linear problem. It's just like the one we just did, and we're going to solve that. So if we take the century deposit data, and here's our pseudo section, and if we take that and invert those data just straight away, we get this image. So this image is really informative, and actually it caused quite a stir when it was first done in the 1990s, because what we see here are two regions of red. So there's an intense region up here, and then there's this broad region up here. And if you look back on the geologic section, those regions correspond with this mineralization zone here and this mineralization zone there. So that's extremely encouraging. So we're going to come back to that. We're first going to now have to do the nonlinear inversion. So in our linear inverse problem, we're minimized this quantity here. We're going to do the same for a nonlinear inverse problem. In the linear problem, we were able to write D is equal to GM, and we had a quadratic regularization, put all that together, that allowed the inverse problem to be really solved in one step. However, if anything's changed, like for instance, if the forward modeling was a nonlinear operation, or phi D changed, was not an L2, but something else, and phi M was not a quadratic, but something else, then you actually have a nonlinear problem. So we've got to contend with that. So in a nonlinear optimization, let's first of all look at something that's quadratic. So let's have a function f of x, and maybe it's written like this. So it has a, f of x looks like this, nicely bowl-shaped. If we want to find the minimum, take the derivative, set it to equal to 0, and we'd be right there. But if f of x is not linear, maybe it's something like this, then it kind of looks like this. So there's a couple minimum, local minimum, maybe global minimum, and these are the guys that we want to find. So how are we going to do that? Well, we're going to appeal to what we had done before with the linear problem, and basically use Newton's method. So what that, in a Newton's method, if we start at some particular location, and so let's suppose we're on this curve, and then we want to get down to ultimately this point there. So we'll make a local quadratic representation of a function. So we'll call that f hat. And then we're going to find the minimum of that and then choose, if I get my cursor back, and we're going to choose this point here. So our quadratic expansion is like this. We'll take the derivative, set that equal to 0, and then we find that we've got a step length, delta x, given by this. So we'll continue to do that and find a place where we're acceptably close to 0, or the solutions don't change. And we also want to make sure that the curvature is up. So for Newton's method, it's, if you have a linear problem, basically arrive there in one step. If you have a nonlinear problem, you're going to iterate. And sometimes we actually want to have, for the perturbation that we've got, we might want to scale it by some alpha that's less than 1. So if we have multivariate functions, now instead of one variable, we actually have a vector. So we still have a Taylor expansion that we can use. So grad here is the gradient operator. And so there's a gradient term, and then there's a second order derivative term, both involving this. So the gradient term is now a vector, okay? And the double or second order gradients, called the Hessian matrix, look something like this. So each element is a second derivative of the ith and the jth element. And the minimum is defined when the gradient is equal to 0 and the Hessian is positive definite. So we're going to proceed in exactly the same way. We're going to start with a solution, and then we've got a system to solve for delta m, and then we'll add a little portion of delta m and make a new update vector. We're going to make a slight cut here on how we represent things. Here's the objective function that we want to minimize. So we can take the gradient of that, and taking the gradient of f gives us what's called the sensitivity matrix. So each element, jij, is the derivative of the ith datum with the jth model element. So that's J, and here it appears as a J transpose. If we do the next level of differentiation to get the Hessian, we get two terms. One is a J transpose J, and then the other is a term that we can often neglect. And so we're just going to represent the Hessian by this J transpose J. And that means that our system of equations really comes as the following: J transpose J plus our regularization, delta M, is equal to right-hand side. And yeah, solve that. So how do we actually go about and do that? We're going to have to start with an initial guess, m naught. We also have to start with an initial beta. And here, in most cases, we're going to start with a very high beta, because we want to have a model that starts off fairly smooth and then gradually gets more structure built into it. So we'll start off with some m naught and a beta naught, and then we'll solve our system here to get back to this Tekanoff curve here. So we're going to solve h delta m is equal to minus g, and get back to here. And then at that point, if we haven't had a satisfactory misfit, we will reduce beta and then proceed along again. And then reduce beta, proceed along again, reduce, proceed along again, until we've got to a point where we're satisfactorily fitting the data. So there's just a ton of ways of addressing this, how you're solving the system, the cooling rate, everything. But one way or another, this is kind of basic to how problems can be solved, and certainly the way we've been doing it. So just in summary, if we had an objective function like this, you have a linear system, you could solve it in one step. Nonlinear system, you're going to be solving systems that include J transpose J, and you're going to be updating, finding a perturbation and updating. I think the thing that maybe is important about this slide is that understanding the linear problem, everything that we've obtained from that is actually valid for the nonlinear problem. So the linear problem, again, kind of forms the basis for things. So our example here, I'm going to now go to the DC resistivity problem. So one of Maxwell's equations for steady state electrostatic was curl E is equal to 0. So that means that the electric field can be written as minus the gradient of potential. We're going to put current into the ground through an electrode. So there's going to be like a point source or a delta function of current. And then, so we've got del dot J is equal to this source. And we also got Ohm's law that J is equal to 1 upon rho E or sigma E. For DC resistivity, we sometimes like to present things in terms of resistivity as opposed to conductivity, kind of eases the communication. So the governing differential equation now looks something like this. So there's a div 1 over rho, or sigma, grad phi is equal to this. So this is the governing differential equation, and we want to solve that numerically. So we're going to need to discretize this. So we're going to have 3 parts. There's going to be the gradient, and there's going to be this mass part, and then there's going to be a divergence. So for the forward model, we need a mesh, and we're going to use a finite volume technique. We're going to put nodes, we're going to put potentials on the nodes up here. Boundary conditions, going to use Neumann conditions like no flux out. And then here's our discrete equations. Remember we had div sigma grad phi. So we've got, here's our gradient, here's the mass matrix, and here's the divergence. All of that gets lumped into one matrix A. So it's A times phi is equal to Q, right-hand side. So that's our forward modeling. For the inversion, we want to ensure positivity and also that resistivity varies in order of magnitude. So we're going to use the log. And there's actually a very nice tutorial about this by Rowan Cockett and co. In 2016, Pixels and Their Neighbors. Okay, so what do we do for evaluating results? Well, it's just the same as in the linear problem. Nothing changes. We want to plot up the Tekanoff curve, just see how phi d is a function of phi m. Maybe we've got a misfit, so we're kind of probably interested in this. But again, all of the details of the Tekanoff curve are applied here. And then the misfit. So we have the observed, predicted, and the normalized misfit. And you're going to evaluate all of this stuff with the models and then come up with something that you think is really useful. So here's a 2D DC resistivity example. It's going to be a pole-dipole array. So we've got these two blocks. Generate the data, add some noise. Here's the apparent resistivity pseudo-section. We're going to start to invert that. Start with a half space and carry out first iteration. And you barely see anything. And if you look at the Tekanoff curve, you're kind of sitting way up here. So you do another iteration or two, get down to iteration 5. Now you see things are starting to pick up. You're getting kind of red and darker green here, but there's still a lot of signal that's left in the normalized misfit. By the time you get to iteration 7, we've technically exceeded our target misfit, and we've got some nice representations of the of the red and the blue block. If you notice in this case here, we probably should have run this a little bit more. We're still the Tekanoff curve hasn't really kind of turned its corner, so there's more signal here that could be obtained up, but that's fine. Now let's go to the century deposit. So we've got the observed data, and we invert that. Now we've got this resistivity section here. So plotted on top of that is the mineralized zones and some faults that were from the geologic structure. And we're going to take a little bit closer look at them. So for that century deposit, then here was the object that we have. I think what we're already seeing here is that there's information about the faulting that is occurring on here, and the DC resistivity is perhaps that's one of its bigger strengths here. So we got the century deposit, and now we want to see what we have got for the DCIP. So now let's do things in the proper order. So the proper order was first the DC resistivity. So we've got that, we invert that, we get this resistivity model. And then we use the IP. So the resistivity here provides the forward mapping for the IP problem, that sensitivity matrix. Now, if we invert that, then we get something that looks like this. So that's actually pretty good. And as I said before, this actually provided a huge amount of information. But can we do better? Yes. We can do better, and we want to do better. Okay, so what information now do we have? Let's just revisit some of these things. So we've got geologic structure, sort of the overall character, the look and feel of what it is you're looking for, whether you got lots of contacts or whether things should be smooth. Maybe we got geologic constraints. We know that there's a boundary someplace, reference model, bounds, multiple data sets. Let's see what we can do for putting that in. So let's go back to the beginning. Here's our generic objective function. And there's actually a lot of stuff that's going on here. So first of all, there's multiple components, and they're all weighted by these alpha parameters. So that provides, those are hyperparameters, provide global weights for these various norms. Then there's individual weightings inside, which can be used for a variety of purposes. There's a reference model. Whoopsie. There's a reference model. And yeah, these combinations actually offer a very large amount of flexibility. The models that I showed you right at the beginning, these inversion models, they're actually generated from the synthetic, but just by changing the alpha parameters. So you can see that if you're going to emphasize horizontal smoothness, which is done by this, you can see how everything is kind of horizontally done. Whereas if you emphasize vertical smoothness, it goes like this. And if you just smallness, closest to some reference model, you get lots of jiggets and jaggets, humps and bumps. So that's the sort of the bulk effect of these global model parameters. I'd like to talk about the reference model, which, remember, I suggested that we do that right at the beginning. This again has many forms. It could be really complex, could be really complicated depending on what you know, or it could be simple. Maybe it's just a half space, but whatever, you do have a reference model always. And that reference model could be incorporated into just the small term. It could also be incorporated into the derivative terms or not. So again, it depends. What do you think you know? Do you think you know about the model, or do you think you know about the derivative of the model? And depending upon those, you can attach particular weights to say that, oh, I'm pretty sure there should be some structure happening at in this region. I'm going to try to make that happen. So these uses of this reference model are quite varied. You add additional information, hypothesis testing. The one I want to focus on just a little bit, it's kind of nice, is sort of depth of investigation. So the interlude to that is this image here, which has got, so this is our straightforward inversion, and it's done with a reference model of 150 ohm meters. The same data, everything exactly the same has been done, inverted, but this time with a reference model of 38 ohm meters. So what you notice here is that in this top one with the reference model of 150, at great depths, essentially the model comes back to 150 ohm meters. In other words, it's just going back to the reference model. The data aren't affecting it that you know of. And down here, the same thing has happened with the 38 ohm meter reference model. You're down into the blue, so these things are around 40 ohm meters. So at these large depths, where we probably don't have, well, we don't have resolution from the survey, the model is just returning to whatever the reference was. So we can quantify that just a little bit by making what we call a depth of investigation index, which is the difference between the models M1 and M2 divided by the difference in the reference models. So in that back case at great depth, M1 returned to M1 ref, M2 returned to M2 ref, so that this, this model becomes 1. If we look at the depth of investigation contours here, so here's a DOI of these values go from 0 to 1. So here's a DOI of a half, kind of comes in about like that. So in this region above here, the reference model is just really not affecting things very much, but in the region below it is. So we can take this boundary and we can superimpose it on the inverted results that we had, and now it comes out to be something like this. We've found that this is extremely important, probably most people in the audience here know this, is that it prevents a lot of kind of unnecessary structure being in there, structure that doesn't have any support from data. And sometimes if you have a big red blob out here and you tell a geologist, oh, don't look at that, it's kind of too late. So truncating things some way is always a good idea. The other thing actually has to do with the weighting functions, W, that come in. Again, they could be used to incorporate confidence on the model or the derivative. It can be used for hypothesis testing. The thing I want to talk about is sensitivity weighting. Let's just consider a linear problem. So let's suppose we had GM is equal to D, and then we're wanting to solve that and minimize like the norm, L2 norm of M. So what's going to try to happen? The easiest way to generate signal is to put some contribution of M very close to regions of a high sensitivity. So if you work with magnetics, for instance, you're very familiar with this. So here's magnetic data. If you just blindly go ahead and apply what we did earlier in our linear inversion, but not use a depth weighting, then the result is going to be a model that's sitting right at the surface, as close as possibly can to the receivers. But with a sensitivity weighting, you get something that looks like this. It'll push it down. It'll push it down at depth, and that might be a little bit more reasonable approximation to what's there. In electromagnetics, and especially when we've got electrodes that we're working with, let's say for the DC problem, if we plot the sensitivity out for just this simple example, so here's a current in here, and then here's a potential electrode. So this is the sensitivity function. So you notice two things. One is that the sensitivities are highest right around the electrode. So they're high here, and high here. The other thing, which is annoying, is that the sensitivities change sign right there. So they get plus and minus. So those two things really conspire to try to A, put material right close to electrode, and B, have a choppiness, like go from high to low, high to low, high to low as you're walking around various electrodes. So you can see that here without sensitivity weightings. You can see how this choppiness that you get. You got sort of high, low, high, low, high, low. And that's not physical. And one way to kind of get rid of that is to put a sensitivity weighting just on these, on the top few layers, especially. And you can generate sensitivity weightings with this quantity here. And then when you carry out the inversion with that, you can see that you've really got rid of that. So it's made it much smoother, and it's made it much more interpretable. I think the last thing that's worth mentioning are bounds. Like we've got often petrophysical information that tells us that rocks can only have this physical property between these bounds or whatever. And also in some cases, even just knowing that things are positive, positivity for susceptibility, for instance, or chargeability can be of importance. So those can be included really straightforwardly with the structure that we have just outlined. It requires an alteration. Instead of just having a perturbation that's h minus 1 times d, you also add a gradient potentially in that can be scaled. So Kelly or Eldad Haber's book are good for that. So let's just look to see what happens there. For enforcing charge positivity with chargeability, this is what we had without chargeability, or sorry, without positivity. And if we add positivity, we get this. So there is not much difference in this case. It's really subtle. You have to look carefully. However, that's not always the case in problems. Here's here's that example for susceptibility. So we've got, this is without positivity, and it's actually negative on here, and then it's kind of broad going down. But with positivity, it looks much more like that, which is what you kind of expect for, in this case, we're looking for a prism. The other thing, and this is work that we're actually really quite excited about, and that is trying to put in more structural information. And this is a very nice example to look at, because what we've got here is we've got a lot of structure. We've got faults in here in which things change rapidly across here. We've got zones of mineralization that are actually pretty thin, right? So if you look back here, so this is, you know, it's there, but it's kind of blurred out, right? And it would be nicer to have something that is more compact. So one way we can do this is take our same objective function, and instead of using two norms here, just use something else, a p norm, where any of the p values goes between 0 and 2. So how does this work, and what do you expect? So if we just have a 2 norm, then the value of that is the value squared. If we have a p norm, we just raise the absolute value to whatever p we have. And if we've got, you know, a model that looks like this, and we evaluate it with different p norms, then you get different numbers. So the ruler length changes for each of those. So the general character, I think, is as insightful as we can get. If you think about p is equal to 2, so now you're looking at squares things. So squares don't like big numbers if they can possibly get away with it. So it tries to, anything that you're minimizing a 2 norm is, tries to put things close to 0. Okay. If you minimize the p is equal to 1, it's kind of like an L1 solution. So you end up with something that's sparse, and the number of non-zero elements are less than or equal to the number of constraints. So that's like the fundamental theorem of linear programming, right? It says that that's what's going to happen. P is equal to 0 gives you what's called a minimum support. So that's actually going to give you the model with just the fewest number of elements, period. So if you kind of go back to our 1D problem, so if we just had the smallest model component, p is equal to 2, this is the result. So notice that it's really trying to make everything close to 0. P is equal to 1, it just wants to have fewer non-zero elements, and there's no big restriction on the height. So the result comes up that looks like this and here, and these all fit the data. P is equal to 0, it wants like the absolute fewest number of non-zero elements, and so you can end up with just basically 2 spikes here. So that's in the model. In the derivative, so we did phi x. Now you're applying the same thing, but now to the derivative. So in this case here, for p equal to 2, wherever my cursor went, for p equal to 2, you end up with something like that. You're trying to make the derivative as close to 0 everywhere. For p equal 1, you want to have a reduced number of places where there's a non-zero derivative. And for p is equal to 0, the absolute minimum number of non-zero derivatives. Excuse me. So here's our LP objective function. It's got 3 values, a PS, a PX, and a PZ. All of those can be between 0 and 2. So I want to give a big shout out here to Dom. he did his PhD work as kind of developing this. For anybody that's worked with L0 norms or anything, an L norm, LP norm that's less than 1, you'll know that it's non-convex. And so getting a solution that actually minimizes is on L equals 0 is a real non-trivial thing. Anyway, here's our observed data, and just a second. Here's our observed data, and we've got a resistivity structure for P is equal to 2. And now if we do that with all of the P values equal to 0, we get something that looks like this. And this is actually quite a significant change. Notice here this blue part in here, this sandstone here is much more confined than it was back here. We've got the red, which is limestone, to be a more contiguous unit. And notice that there's no red in here. So in just the L2, that was red. So this now comes out to be, pure green in this whole area, which is kind of what we wanted. And so I'm going to flip back and forth here. So in this diagram here, we've color coded the sort of the limestone and the sandstones up on here. And so you can kind of flip back and forth and just see how nicely the inversion result is fitting, and especially this fault that we have in here is very crisp compared to here. So that's good. Those are all really kind of positive attributes. And now if we're going to do the inversion for the IP data, let's do it twice. So let's first of all do it with P is equal to 2. So this is what we showed you before. So the Dc resistivity P equal 2 is that. And now we use the sensitivities from that, sensitivities from that to do the IP, and we get this. Which wasn't bad. It's actually pretty nice. But if we now do the DC with the LP inversion, get a better output, and now we do the IP, it's really improved things. It's really tightened things up. So look at where the mineralized zone is here, and the offset along the fault. That's just like a seriously good result. So lastly, I just want to kind of finish up with this. It's a question about like what other information is available. So even on this diagram here, I mean, we'll have a drill hole, and so we'll know something about the lithology of the rocks. We'll know something about the petrophysics. Know something about depths. We've got a lot of other information to put in. So we've got drill cores and we've got physical property values, and the question is, okay, how do we put all those things together? Well, here's the work that we've been doing most recently, and here a big shout out to Thibaut Astig, he did this for his PhD, and we're going to continue this while he's a postdoc, and it's also going to form a part of a number of other projects, because I think this is one of the biggest steps forward that I've seen in a long time to really enhance our geophysical inversions. So what do we have? We've got geophysical data over here. Could be multi-surveys, whatever we got. we've got some petrophysical information from here, and we've got some geologic information. So we want to somehow put all of that in. If you kind of try to dump it into one hopper all at once, it's a bit overwhelming. So what Thibaut has done is say, okay, let's divide this thing up into 3 parts. These are actually going to be 3 sequential inversions that are done. In fact, 2 of these are Bayesian, and this one is deterministic. So we're going to kind of continue to go around here to do the petrophysical characterization, geologic data, and somehow put that information into the geophysical inversion and get an updated model. And the part that I think is really exciting about this and extremely useful is that this petrophysical characterization, the geologic identification, they're all coded into the smallest model component. So this thing that we have been carrying with us throughout the whole of this inversion now gets modified so that we continually update a reference model and solve the, the inverse problem in such a way that this other information is there. And the differences between doing something like this and not are really quite large, and we're excited to kind of go forth with this. So that's it. I want to thank everybody for attending. This is great, and thanks, Alan, for asking me. I want to thank the SimPeg community. Everything that you've seen in here has been really developed by the open source resources in SimPeg, and yeah, that has just really eased our ability to get research done and to share it. The inversion resources, they're all available through CurveNote. I've talked before about just how impressed I am with this. It's going to allow all of us to share information and to work cooperatively together and really advance, I think, the community as a whole in a much easier way than has been possible. And yeah, so with that, I just put a big little plug in. Next week, well, Lindsay will be talking, so she'll have some real substantive stuff to say with respect to how to go from equations to through SimPeg and get results. How to turn equations into software. So you'll be excited to hear about that, and I will also be. Anyway, thank you very much, and yeah, happy to answer some questions.
Well, thank you, Doug, on behalf of all the 170 people that got most of your talk. Absolutely wonderful. We got some questions rolling in, and what I'd like to do, Doug, is you can probably see the questions, but I want to read them out.
No, I can't.
Well, there's a Q&A at the bottom of your screen or top of your screen. You should see Q&A.
Oh, do I have to stop sharing?
Not necessarily. Maybe. Anyway, yeah.
I see you. This is exciting. Magnetotelluric methods and a spoon. Let's see. Oh, so in the chat?
No, there's a Q&A box. It might be.
Oh, I see. Q&A. Gary, I got it.
Yeah, I got you. Okay. So there's quite a few questions rolled in. Some of them I'll paraphrase because they're quite long. The very first one is from Firidun Sharifi, who's asking about whether the script is available. And I think the answer to that is yes, of course. You made it clear that all of your all of this work that you presented is available
Yes, that's right. The notebooks are all available, and yeah, actually, and Lindsay will talk a lot more next week about just SIMPEG and all of the open source resources that exist.
And the next question is a rather long one by Sergio Espinoza, and I don't propose to put this to you because it relates to physics rather than to inversion, and it's to do with charges around 3D bodies. I guess the one question I could ask of you related to Sergio's question is, how do you deal with 3D when you're doing 2D inversion?
Oh, I guess I don't know the answer to that, because we've actually in many cases kind of tried to err on going to 3D. So I guess for magnetotellurics, we are developing a 2D inversion, but really the things that we've been concentrating are 1D and 3D. The 2D, we've always felt for many of the electromagnetic problems, there's just too many assumptions that have to go in, and there's too many, it's just too much computation that's required with sometimes a lot of transforms that are going in, and it's almost as much work to go into 3D. So 1D is actually sometimes really powerful on a first stage through, and then I think we just got to be in 3D.
We have a very interesting question from Dave McCurdy, who used to be in our field but moved into metamaterials. And Dave asks, this is a more general question and not limited to geophysics. I work on metamaterials, and fascinating things can happen when the permeabilities and permittivities are negative. Clearly, positivity constraints will not apply here. Do you work in other fields of physics and engineering?
Well, that's an interesting phenomena, right? With problems with physical properties that we tend to think of being positive going negative. We haven't been investigating those per se, but there's really nothing in the methodologies that been working with that would prevent us from doing that. It would be, what did they, I was trying to remember, there's a name for kind of cloaking. You make things invisible by having negative electrical permittivity, I think it was. And yeah, it's interesting. And yeah, the physics there, and we be interesting to model things. Actually, if David's got a kind of an example that I'd like to, like a little test case or something like that to work with, that might be really fun. That would be really fun. And as we're developing resources on electromagnetics, and we're trying to develop Jupyter notebooks and curve notes so that people can contribute, maybe David would like to start one off about this, and we could see where it goes.
Yeah, there you go, David. Wonderful invitation. So Sayed is asking about this basically trade-off curve. Thank you very much for your informative presentation. Which way is better for selection of beta? 5-star D or choosing beta the knee point of the trade-off curve? Besides, in many cases I've experienced the trade-off curve could not even reach the knee point, even if very small or even 0 beta.
Well, there's actually quite a bit in that there, and those are pretty general. Some of those are kind of general questions, and every data set has got its own little nuances and things like that. I'll make a couple of comments. Generally, we always try to make a fairly substantial portion of that that trade-off curve. So our first kick at the cat as to when to stop is, phi d to be some target value, usually connected with number of data, and that's a pretty reasonable one. But sometimes you really want to continue on, solve the problem for smaller betas, at least so long as you're not building up excessive structure. So you really want to have a number of models and also view the Tekanoff curve kind of holistically to kind of see, okay, where do I stop? Sometimes you might not even be able to get close to what you'd consider to be a target misfit, but maybe that's because your uncertainties were really incorrectly input. And the other thing about the knee of the trade-off curve, really some of the mathematical arguments for that are, even if you look in quadratic space, we have that sort of standard Tekanoff curve. If you plot the misfit and the model norm on linear scales, generally we apply it on logarithmic scales, but you might actually take the same example that you've got, plot misfit and model norm on a linear scale, and then see what that looks like.
Mohammed asks about choosing the resistivity value of the reference model. Is the forward model enough, or should we run an inversion? And then there's a second question about negative value of the trade-off parameter. If yes, what does is there a negative value of a trade-off parameter?
No. Yeah, trade-off parameter is defined between 0 and infinity. Yeah, I'm not really sure what he means. You really want to take your a priori information, use that, and you generate your reference model. It might be simple or complex, and then you want to forward model that and see how it compares with the data. In general, that's not going to satisfy the data. But what I was meaning by doing that comparison is that very often you get like wildly different numbers. You've got data numbers that are 10,000, and you do a forward modeling and you get 1. So maybe there's a scale factor of 10,000 there that you need to take care of. So though it's doing that forward modeling from the reference model is just a little bit of a sanity check to kind of make sure that things are looking approximately right. But then your chances of you finding something that fit the data are pretty small, so that you go ahead then and do the inversion.
Eugene Kiev asks, it says, "Hi Doug, thanks for a terrific talk. During my work, some of the raw data is missing the variance, is missing the errors. Thus, the data misfit term can't be constructed to follow chi-square distribution, which means the regularization factor cannot be chosen to let the data misfit be around n. In this situation, do you have any suggestion for choosing the regularization factor? The L curve seems a bit empirical."
When you collect field data, it's unfortunate, but you're never provided with an uncertainty that's actually useful for you in the inversion. And what I tried to illustrate or show in the talk was that these uncertainties that you have in the inversion have to take into account everything that your forward modeling that you're using is inadequate for representing the true data. So what you have to do in general cases is like, okay, we've got some data here. We really don't know what the errors are. So I'm going to make some kind of reasonable guess, and that guess is going to be, perhaps a percentage plus a floor, and then you try it with that, and you might decide on the basis of those results, like whether you've actually done a good job or you have a poor job. Sometimes by looking at the statistics of the errors or the misfits between observed and predicted, you can get some idea of maybe there's some outliers or maybe there's something else that's going on. But yeah, unfortunately, we never know what the errors are to apply, so it's a bit of a guessing game.
I think it's actually worse than a guessing game in as much as a data guy, I will provide you with errors that are impossible to model because errors are too small for the physics. Neighboring frequencies that just cannot be modeled. And so that's why you introduce an error floor.
Right. And there's lots of contractors there will provide uncertainties based upon repeatability. And, that's one that provides, provides a number, but that's usually a lower bound to what you really are looking for, because there's just so many other areas that, the difference between what's really out there and what you are mathematically modeling is discrepant.
Well, it's 2:30 here, well, where I am in Ottawa. It's been 2 hours, Doug, and I think perhaps we should call it a day, if you don't mind. There's some more questions, but those people could write to you directly, if that's okay with you.
Absolutely.
Yeah, unless you see one question that you particularly like to address.
No, I was actually captivated by your picture holding up the book and your spoon. I was trying to read what was on the spoon, but it suggested to me that maybe it's time to have some soup or something.
No, that spoon, I got the award of the wooden spoon. You might know the wooden spoon, right? You get the award of the wooden spoon if you're last. I didn't
know that.
I provided the last chapter to my MT book, so I got awarded the wooden spoon by Cambridge University Press.
Fair enough. Yeah, I'd be happy to answer other questions if people would like. So, I mean, they can just send them to me. But
okay, in that case, I'll sign off by just reminding everybody, please come and visit us next week. We'll be an hour and a half earlier, where we'll have Lindsay, who continue on all the fabulous things Doug's told us, and how to work with all these ideas in code. So goodbye, everybody. Thanks very much again, Doug. It's been wonderful. Stay safe, and we'll see you next week.
Okay, thanks, Alan, for arranging, and goodbye to everybody. Thanks for joining.